Welcome. Today I'd like to talk about a possible framework, a possible variational framework for the Helfrich energy. And the framework that we're choosing is the so-called geometric measure theory, or in short, GMT. Okay, and for that, try to give you a little overview of GMT and how to apply this to the Helfrich energy. As a short reminder, what is it what we want to do? We want to minimize the Helfrich energy. The Helfrich energy is given as this integral over here. So what do we have here? We have the scalar mean curvature of a given oriented immersion, and we calculate the L2 difference to a given parameter called spontaneous curvature. And we want to minimize this guy under given area and given enclosed volume. So we do not have a boundary, for example. Okay, and how do you do that usually? By the direct method of variational calculus. How does it work? It works like this. You take a sequence Fm, which satisfies that the energy of these Fms actually goes to the infimum of the Helfrich energy under, of course, these constraints. So fixed area, enclosed volume, fixated topology sigma, and so on and so forth. So, and then of course what we want to do is we want to find a limit. So, and the limit is our minimizer. This is our goal. We want to find such a minimizer. And how do we proceed now? Of course, you somehow have to find a convergent subsequence of these FMs. This is by no means trivial, and the framework that we are trying to establish here is one which is called geometric measure theory. And measure theory because of this, because we want to reformulate these FMs, these immersions, as Radon measures. So then we can use good compactness theorems from measure theory. Okay, this is essentially the outline for this talk. Let us dive straight in. Oh, yeah. The first thing is, how do we get from an immersion to a varifold or a Radon measure? So a varifold is essentially a Radon measure. I will explain what it is precisely later in this talk. But for now, just the basic idea. So an immersion itself can have self-intersections. So the red line is one part of the immersion and the black line is another part of the immersion. And they're now intersecting here in this middle part. And what we do is we define so-called densities. So on this red line where there's no intersections, we say density should be 1. And if we have an intersection, the density should be the number of these intersections. So in our case, 2. And now, how do we define the Radon measure corresponding to this immersion? So we calculate, so we define what this Radon measure mu for given set A is, integrate over A intersected with the image of F over this defined density above here with respect to this Hausdorff measure. If you do not know what this two-dimensional Hausdorff measure is, do not worry, just think of it as one way to define a two-dimensional area or volume measure in Rn. Yeah, and now this guy over here is actually an example of a rectifiable varifold. Before we proceed, you may have noticed this little comment down here. In this talk, I try to give you some explicit references for these kinds of definitions and theorems that I will give. And in the end of the talk, I will talk about these references in more detail and give some recommendations. Okay, back to the talk. So now what we have is, instead of working with an immersion, we have a radon measure now. And why is this useful? Because now we can define a convergence for these immersions, essentially. And how do you do that? By the so-called Riese Representation theorem. This is a theorem which works on the on the set of continuous functions with compact support, and it establishes a one-to-one connection between the Radon measures and the linear continuous functionals on this set over here. And this one-to-one connection works essentially like this. If you're given a Radon measure mu, you define a linear functional just by integrating over a given function coming from this set over here. This defines a linear continuous functional. If you have a linear functional, you can define a Radon measure like this above here for a given open set U. And then, of course, since you want to have a Radon measure, and Radon measures are uniquely defined by giving the values on all open sets, you have a Radon measure. And this now opens up the possibility for a convergence definition. What we're doing is, we are defining the convergence of Radon measures as pointwise convergence of our linear functionals L, which correspond to our Radon measures. So if we write this down, what does it mean? We take an arbitrary test function phi coming from the set of all continuous functions with compact support. We integrate over our mu m's, and if these guys actually converge to integral phi d mu, then we say that the mu m's converge to mu in the so-called weak star sense, or in the pointwise sense for these linear functionals. Okay, so now we have a convergence, and can we actually get compactness? The answer is yes. There's a very general compactness results for Radon measures, which again stems from this duality, from this one-to-one connection from the Riese Representation theorem. This is coming from essentially the Banach-Arloglu theorem, and the result looks as follows. So, if you have a sequence mu m, and you evaluate them for a given compact set, which has to be arbitrary but fixated, and then this guy is bounded, independent of m, but this bound of course may depend on k, but independent of m, then you can extract a weak star convergent subsequence. So this is not hard to check for our problem, but the next problem is actually, now we have convergence as Radon measures, but is the limit still something which is geometrically speaking makes sense? So I've written down here a little sketch. What may happen, for example, is that in the limit you leave your assigned dimension. So this one-dimensional object here would have a part which is two-dimensional. It may also degenerate and become zero-dimensional or something else. So a lot of things can happen because this convergence, this weak star convergence, is a very weak convergence. So now we have to establish what the limit, if the limit has some kind of geometric properties. And for this, I like to define what a general varifold is. And for this, to define that, we need to define what the Grassmanian is. The Grassmanian is essentially the set of all subspaces of a given dimension. So in our case, and how do you define this in a good sense? You take a linear subspace X, and then you take the corresponding orthogonal projection pi x, and then you just say, okay, the set of all subspaces of a given dimension is the set of all orthogonal projections. Why do we use these orthogonal projections? Because of course we want to have some kind of topology on the Grassmanian. And the topology for these pi x is straightforward. For one possible way to define a metric on this guy is to write down the corresponding matrix for these orthogonal projections and define the difference between two orthogonal projections, the distance between the two orthogonal projections, as just the distance between these two matrices. Okay. Now we've established what a Grassmanian is. Now we can establish what a general varifold is. A general varifold is a Radon measure on Rn times this Grassmanian over here. Okay, but of course, this is just a very general object. We still want some geometry, so we need tangential spaces, essentially. A good geometric object, in differential geometry at least, should have some notion of tangential space. And for this, we need to define what the so-called rectifiable set is. So a set which essentially admits a tangential space. How can you do that? You call a set M n-rectifiable if it is lying in a countable union of nj's, and if j is bigger or equal to 1, these nj's shall be C1 submanifolds, and for j equal to 0, this should be a set of measure 0. So in this n0, you can basically put in all your singularities, your kings, everything where strange things might happen, but it shouldn't become too strange. The dimension should not be too big for this guy. Okay. How do we get a subspace out of that? So, of course, we do not get subspaces, tangent spaces everywhere, but almost everywhere, Hn almost everywhere. Take an x coming from M, then you can define the tangent space Txm by the corresponding tangent space of Nj. This x here has to lie in 1, 2, or 3 of these Nj's here, and then you take the tangent space of the corresponding Nj in which the x lies. And now we know what a rectifiable set is. Rectifiable sets have tangent spaces, and then we can define the corresponding notion of rectifiable varifold. A rectifiable varifold mu is defined like this. So you integrate over a given density, and you integrate over the rectifiable set intersected with your given set A. And you integrate, of course, with respect to the n-dimensional Hausdorff measure. So this is an example of a rectifiable varifold. And since I've told you that you want to track tangent spaces, we can actually define a general varifold corresponding to that as well. So we're doing this with the Riese Representation theorem. So we take a test function phi coming from the set of all continuous functions with compact support on Rm times the Grassmanian. And then we can define a Radon measure on this ZRM times the Grassmanian by integrating over this test function phi. And what do we plug in? The first variable, of course, this x over which we integrate. And then in the second variable, we plug in the corresponding tangential space of M. And then we integrate this guy over M itself. Okay. This would define a general varifold and a general rectifiable varifold, which also tracks the tangent space. This is very good. This is what is done in general. And then, of course, imagine now we have a limit. Then we have to actually define what the Helfrich energy for this limit is. So imagine you have a varifold, and this is the limit of your minimizing sequence. And now this limit has to, there you want to calculate what the Helfrich energy is. And to calculate this, you need a mean curvature. And what you do now to define a mean curvature is basically you say that it has that the varifold has to satisfy a partial integration. So, what does it mean? If you take a test function phi and you calculate this divergence of phi with respect to the tangential space of the varifold, and this is actually some given function h times phi, then you say that this given function h is a mean curvature vector of the varifold. This equality here stems from the Gauss theorem for submanifolds. Usually there would be another term corresponding with the boundary of this submanifold, but since we're working with closed immersions which do not have a boundary, we can neglect this term here. So what we're essentially saying is we define what a mean curvature vector is just by requiring the varifold to satisfy a partial integration. Okay, now we have a mean curvature. Very good, we can work with that. Now we wanted to define what the Helfrich energy for this guy actually is. Let's take a closer look to the Helfrich energy for immersions to work out the details correctly. For immersions, it was like this. We have a given mean curvature vector minus our parameter, which is called spontaneous curvature, times the normal. Okay, now we have a problem. We do not have a normal for a varifold. We are only tracking tangential spaces. We are not tracking orientations. And this is indeed a problem which has to be alleviated before our variation framework is complete. And how do we do that? The essential idea is to replace this Grassmanian, so the space of all subspaces, with the space of all orientations. And this idea goes back to Hutchinson, and he essentially looked at the oriented Grassmanian, which is the set of all possible orientations for a two-dimensional subspace in R3. And this is given by an orthonormal basis, tau 1, tau 2. And this guy, of course, corresponds to the unit sphere just by taking the cross product from tau 1 with tau 2. And this will give you something like this. So these blue arrows here represent the basis of this gray tangential space. And this red arrow here is then the corresponding normal given by this orientation. And now how can we proceed? Now we have oriented varifolds. Now how do we want to define what an oriented varifold is? And we're doing this essentially as we've done it above. So we take the Riese Representation theorem and use this as a method to define a Varifold or a Radon measure on R3 times our oriented Grassmanian. So, if we want to use Riese's representation theorem, we will have to use an arbitrary test function phi, which is continuous with compact support on R3 times the oriented Grassmanian. And then we take an orientation on a tangential space of a rectifiable set M. And then we define what an oriented varifold actually is. An oriented rectifiable varifold actually is. So we plug in a rectifiable set, two densities, and the given orientation. Why do we need two densities? We need one density for the orientation aligning to the given orientation psi, and one with a minus sign. So, in the first term over here, the orientation is the same as the given orientation, and therefore we're using the density theta plus. If the density is opposite to the given orientation, we plug in a minus sign here to reflect that, and we're using the density theta minus. And this is an oriented rectifiable varifold. So, as I told you above, now we need to be a bit more careful when we go from an immersion to a varifold, because now we want to respect the orientation as well. So, how do you do that? You take an immersion, a given orientation on the image of this immersion, and then you basically control the orientation by writing down the correct densities. So f of sigma is the corresponding rectifiable set, psi f is the orientation, which we've just basically chosen randomly. It just should be measurable. This is not a big problem. And then we define the correct densities. How do you define the correct densities? In the following way. So sigma should be oriented. Without it, it wouldn't make any sense to write down the kinematic energy at all. And we take this tau here is the orientation of this manifold. And then the immersion F transports this orientation to another orientation of the tangential space over here, which is given like this. And if this orientation coming from F aligns with the given orientation, psi F, we basically add 1 to theta plus, so the orientation, so the density theta plus, which aligns to psi F. And if they do not align, they will align to the negative orientation of psi F. Then we add 1 to theta minus. Okay, and this is a little sketch down here which shows you how this works. So psi F over here is going up on this red line, and on this black line over here, since psi F cannot distinguish between a red line and the black line if they coincide, we just choose this to go down. But this means that on this intersection, we actually have two orientations. One which is opposite of psi F, coming from this red line, and one which is psi F itself, coming from this black line. So for this red line, we need to have theta minus equal to 1, and for this black line, theta plus equal to 1. Okay, and now we can define what the Helfrich energy for oriented varifolds actually is. So H subscript oriented varifold is just the mean curvature vector which we have defined above. There's no real difference there. Psi over here is orientation, and this star operator here is called the Hodge star dual, which essentially transforms this psi to the corresponding normal vector of the subspace. Or in more basic terms, it is a cross product between the orthonormal basis vectors. Okay, and this is the more general formulation, but we can also write this down with densities and a rectifiable set, which then looks like this. So if psi itself, if we have a positive orientation, then we do not change this sign over here. And of course, then we work with theta plus. If we change the orientation, then this minus sign here changes to a plus sign, and we integrate over theta minus. Why is this all possible for varifolds? At least for integral varifolds, so theta plus and theta minus have to be natural numbers. There's this theorem by Bracke, which is quite deep, which essentially says that the mean curvature vector is orthonormal to the tangential space. So that means that this guy over here actually makes sense in a good way. Okay, now this is the Helfrich energy for oriented varifolds. And now we can use a compactness result by Hutchinson for these oriented varifolds, which will guarantee that the limit is again integral, which means that the densities are natural numbers, and the oriented varifold is rectifiable. So we have tangent spaces, so we have geometry. Let's take a closer look at this compactness results. So we have these four prerequisites. The first one is a bound on the mass. That means basically if you integrate over the densities, then this guy should be bounded, independent of the sequence parameter m. The next step, the next one is we need a control on the mean curvature. For example, this would be enough. The next step would be some control on the boundary. Since we do not have any boundary here, this is moot in our case, so I do not go into detail here. But this point would be a bit more technical. You would need to know what currents are, which is beyond the scope of this talk. But since we do not have any boundary, we don't have to worry about this. The next part is these varifolds have to be integral. So, the densities have to be natural numbers, and the varifolds have to be rectifiable, which is not a problem because our varifolds correspond to immersions. And then we can extract a converging subsequence, and the limit is again an oriented integral varifold. That means the densities are natural numbers and the underlying set is rectifiable. Okay, and this is essentially the variation framework given by geometric measure theory. And at the back of this is this compactness theorem. Okay. This is essentially everything that I wanted to tell you. But now let's take a closer look at what is coming up next. So the next video, we'll get into the more details of the Helfrich energy itself. One important question is, if now we have a limit, is this limit actually a minimizer? Just because the minimizing sequence tends to the infimum does not guarantee that the limit attains this infimum. For this you would usually need some kind of lower semi-continuity. And this is a central part of the next video that I like to present. And another question is, now we have an oriented varifold, an integral oriented varifold, which is good, of course. But is it again an immersion? Can we get more regularity out of it? As it turns out, yes. And the method I like to present actually connects these 2 points intimately. And but this is for the next video. For this video, I'd promised you to talk a little bit about literature and give you some recommendations. So the first recommendation is a textbook by Francesco Maggi called Sets of Finite Parameter and Geometric Variational Problems. A very good beginner-friendly introduction to geometric measure theory. I highly recommend starting with this book. And accompanying with this book is a very good choice would be Evans and Garaipi. Here the foundations are explained very well as well. But if you take a look at these books, you will sooner or later notice that they do not mention varifolds at all. If you want to learn more about varifolds and general varifolds and so on and so forth, you will have to take a look at Lee and Simon's lecture notes, and which are excellent, but a bit more advanced. So as a primer, I'd recommend Maggi's book, and if you want to know a bit more about varifolds, read Lee and Simon's book. I mentioned in my talk Hutchinson's oriented varifolds. As far as I know, these do not have been incorporated in any kind of good textbook yet. But the original paper is very well written. Just take a look at that one. If you know what a varifold is, this paper is a very easy read. Very good, I recommend that one. And no list of literature would be complete without mentioning Federer's Geometric Measure Theory textbook. The problem with this book over here is that it is not suitable for beginners. It is very advanced, very technically written. But on the other hand, there's so much in it. There are so many. This is a treasure trove of information. If you want to really know something very specific, for example, for the Hausdorff measure, chances are high Federer has worked it out in his book somewhere. So this guy here is a back reference if you need some very specific information. Maggi has a primer, and Lee and Simon as your mainstay textbook. This is what I recommend. Okay. Last but not least, I should tell you about some other variational frameworks for the Scalar-Helfrich energy. The geometric measure theory is also called ambient approach because we need an ambient space to define our Radon measures. If we do not have an ambient space, we cannot define a Radon measure in a good way. The alternative would be to use parameterization. So we've looked at immersions F coming from a sigma into R3, and if you work directly with these Fs, this is also possible. Tristan Rivière worked out how to do that, and this approach has also been used in a variety of cases. And here I like to basically encourage you to check out Christian Scharrer's video. He used this parametric approach to also attack some of these Cahnam-Helfrich variational problems. And with that, I'd like to thank you for your attention. Maybe we'll see each other in the next video. Bye bye and have a nice day.